My name is Ben Brewer and I'm a principal consultant at DMV, and I'm actually signed in with Tony's link, so you'll just have to ignore the name on my video for now, but thank you. So I'm here today to present our work so far on the SF6 whole life strategy, this discovery phase show and tell. Next slide, please. So outline agenda for the day. For this 15-minute presentation, first of all, we'll look at SF6 use in the power sector across GB. We'll run through a quick project overview as to what we've been doing so far. And then we'll look ahead and at the next steps in terms of taking this forward to alpha phase. And then we'll invite questions through a general Q&A for the last part of the session. The next slide, please. So SF6, what is SF6? It is sulphur hexafluoride. It's one of the most potent greenhouse gases that we know. Its high atmospheric stability and ability to trap infrared radiation means that it's far more potent in terms of warming the Earth's atmosphere than carbon dioxide over longer periods of time. Indeed, across transmission networks and distribution networks, we estimate that after technical losses, SF6 leakage from assets is one of the highest contributory factors to greenhouse gas emissions across networks. And to put the potency into perspective, you can see on the bottom left with the small blue square, this is 1 kilogram of SF6, and it's equivalent to 24,300 kilograms of CO2. So it's a very high potency gas. Annual emissions of SF6 between 2012 and 2022 rose by 47% as networks installed more GIS, gas insulated switchgear. Annual global SF6 emissions were equivalent to yearly CO2 emissions from 44 million passenger cars. And to put that into perspective, in the UK, there are 33 million cars on the road today. This is also the equivalent of 103 million tons of coal, and National Grid has the ambition to reduce SF6 emissions by 50% by 2030, working towards complete removal of SF6 gas from electrical assets by 2050. Next slide, please. So just a brief overview of the project. In the italics is our pitch statement, if you like. So we are developing an economic, efficient and holistic replacement strategy for SF6 free, to be SF6 free, that will support GB's ambition to facilitate a net zero and resilient energy system. Partners on this project is main lead is National Grid, electricity transmission, supported with project partners who are DNV, University of Manchester and SSCN. Key activities in the discovery phase are to, well, and potential future stages are to develop and assess options that are available for replacing SF6 in existing assets and going forward, and to develop a high-level plan of the testing that's required to validate the replacement strategies that are recommended through this project, and to undertake a techno-economic analysis to underpin this strategy in terms of identifying when and where necessary interventions should be taking place in networks when replacing SF6 gas. And this is targeting the Innovation Challenge 3, which is improving energy system resilience and robustness. Next slide, please. So what have we been doing today? We've held a combination of in-person workshops at University of Manchester, where the project partners have come together. And we've held a number of online meetings as well, as weekly recurring. And in these meetings, we've been refining the work packages and working through some of the more technical detail, reviewing the various work streams on the project as well, and just keeping track of project program and reflecting on deliverables as well. We've been gathering and processing SF6 leakage rate data from networks, And we've been developing an understanding of which assets require intervention and quantifying those leakage rates as well. In terms of our methodology, we've been defining that at this stage and also carrying out some techno-economic analysis. So for instance, we've selected two substations which are national grid sites with quite different profiles in terms of the age of the assets there and the SF6 leakage rate from those assets as well. And we've been preparing a cost benefit, a techno-economic analysis, which captures parameters such as carbon credits and cost of carbon from HM Treasury Green Book, for instance. And we've been calculating the net present value based on the application of different intervention options. So whether it's retrofill, leak repair, refurbishment, or early replacement of those assets. And we put together a comparison looking at those different interventions across the forthcoming years as well. And then finally, we've been scoping out the next phase of the project as well and preparing an alpha phase submission application. Next slide, please. Okay, so I'd just like to hand over to Tony. Thank you.
So carry on from Ben then. So first of all, just to cover what are the mains of SF6 replacement interventions. Really, you can broadly divide into three groups. So we start with the first one on the left-hand side of the screen, which is new build. So effectively, this is to decommission the entire SF6 substations and replace it with a new substation equipment using a new gas that's optimized for those new equipment. So the first one was actually installed in the UK back in 2017. So already about 5 years of service experience already. So we found that the leak rate was marginally higher than the equivalent SF6 leak rate. So this was in Sellenge, UK. But the problem with this approach is cost and time consuming. So to put into perspective, a complete new build could cost in excess of 100 million. And there are over 100 gas insulated substations using SF6 in National Grid's inventory. So it's quite costly to do a complete replacement of all those substations. And it's also a time issue as well. Each of this GIS can take years to complete. So the one in the middle is some of the research that was initiated actually at Manchester, which is look at can we develop a retrofill solutions. Like the name suggests, is to take the SF6 out of existing legacy equipment and to replace it with a more environmentally friendly alternative that obviously with a significantly lower environmental impact. So it's found there was a solution, optimized solution that can give up to 99% reduction in the equivalent carbon footprint, and basically without modifying the rated pressure or having to open the equipment. So literally gas out, new gas in. We'll have to change the density meter and also make some small modification to the desiccant, which don't require the opening of the bus, which then becomes quite costly. So the first retrofill operation in the world was again accomplished in the UK in Richborough, Kent by National Grid, which was energized in December 2021. So still sort of early days for these two solutions. The last one is leak repair. So there are certain, so the key thing to remember with retrofill is the costing is mainly just the gas and the labor. So the cost is then it's only a few million rather than excess of tens of millions or even over 100 million. But retrofill doesn't work on all of the legacy equipment because there's compatibility issues. At the end of the day, we're putting a new gas into equipment that's optimized for SF6. So certain equipment will end up being too leaky to trial the retrofill solutions. So what National Grid has done in parallel is working with other partners to develop leak repair solutions. So so initial pilot trials was already being done in the DSITE Center for Innovations. So this is using innovative sort of molten metal manipulation technologies developed by Raw Water. So you can see from the photo, so the bore valve, so what effectively you see there is solder ions on top of the bore valve, and that basically seals majority of the gas leak from SF6. So that has been successfully trialed in the Norwich and Sizewell substations. So those are the sort of three main intervention approach. Next slide, please. So then we kind of look into the leakage rate insight. So how do we decide which substation to use, which approach? So the key thing to point out, the leakage rate here is a top up in kilograms converted into leakage rate, because National Grid hasn't got leakage monitoring for every single substations over, since 1960s. So these are top up in SF6 in kilograms converted based on the total inventory data. What we can broadly see is the older assets are more leaky and the modern assets are less leaky. But with time, the leakage rate will naturally increase for these equipment. And you can see that majority of the assets actually installed since 2010, so in the sort of last 10 to 15 years. So really the 4.6% of asset that's kind of reaching the end, fast approaching the end of life. The reality is you can probably look for one-off permanent leak repair solutions to extend the life a few more years until they're ready for full replacement. The one, if I go straight to the 66%, which are in the early stage of the asset lifetimes, they're really not suitable for a complete replacement because they can still function for another 40 years or 50 years before final replacement. So it would be very costly and ineffective to replace them now. So they're potentially more suitable for retrofit. The ones in the middle, a decision would have to be made on a case-by-case basis. Some might be more suitable for the leak repair, and some might be for retrofit, depending on the leakage profiles. So that's a broad, kind of quick insight into the leakage rate on all of the National Grid's SF6 assets here. Next slide, please. So just to touch on to the sort of the key insights and benefits of this project. So the project is really about to enable more efficient and timely interventions on SF6 equipment to identify that optimal approach based on the difference of asset types. So as mentioned previously, a complete rebuild is very, very expensive and time consuming. And to do that for 100 substations before 2050 would be impossible for National Grid. So really we have to identify different approaches, which is something that we've done in the discovery phase. Then is the techno-economical analysis to demonstrate that benefit through the reduction in carbon credit costs, but it's also the societal cost of a more low carbon approach going forward, associated with the retrofill, leak repair, but also early replacement ahead of the end of the lifetimes. So we look at the use of automations in the gathering and analysis of SF6 data, because as I mentioned, at the moment, the recorded data is top up of SF6 and converting that into a leakage rate, which is not indicative of an actual leakage profile of the asset. So having that would allow us to make a better assessment to determine the optimal interventions. As mentioned, there are certain solutions available already, and they tend to be in mixtures, so 2 or 3 gases are mixed together as a replacement of SF6. So for those ones, there's a problem when it comes to the site handlings, as more and more alternative being used. So the mixture ratio could be different. That could lead to cross-contaminations or maloperations, where procedures or technology must be developed to safeguard against that. And as we phase out SF6, removing thousands of tons of SF6 from the network, then we really ought to find alternative ways to dispose SF6. At the moment, just literally throw the SF6 bottles into a furnace and burn it at 1,200 degrees, which is quite a highly carbon-intensive approach to destroy it. So next phase of the demonstration work was to look at the laboratory scale testing to demonstrate the low carbon approaches possible. And finally, the last one, system access. If we have areas like London with a very high density of GIS due to space constraints, then we can't just take all the substations offline. So we'll have to look at evaluating the system access for different substations to ensure that we can carry out the SF6 interventions in a timely manner. And I'll pass it back to Ben for the last few slides here.
Thanks, Tony. So we're approaching the final stages of discovery phase. We're preparing the report at the moment. And then, as I mentioned earlier, we're also preparing an application for the alpha phase as well, where we really look to take this to the next level of detail, exploring opportunities and barriers to the various SF6 interventions that we've defined in the discovery phase. We'll take a machine learning approach to SF6 leakage assessment and look at the practicalities of handling site gases, gases on site in terms of removal from assets, and laboratory testing of disposal methods as well, in terms of destroying the SF6 or recycling, and understanding system access implications, as Tony explained. And then if this was to progress to the beta stage, then this would include a large-scale demonstration of interventions, of the effectiveness of those interventions in situ on sites, and would sort of culminate in developing a holistic rollout strategy across other eligible sites as well. And then from that stage, we would anticipate that it would be a business as usual process to implement that strategy across networks. And all through this process, we'll be disseminating the findings as well as we go along. Next slide, please. So in terms of next steps, just finalizing the discovery phase report and techno-economic analysis, on preparing a submission for the alpha phase proposal as well, and building on the learnings of the discovery phase. Sean Coleman is project sponsor from National Grid Electricity Transmission, so feel free to reach out on further details on this project, and you can see the overall timeline there of the alpha phase as well. And I think that's all I have, so I'd like to invite questions from attendees.
Thank you so much both for a very interesting presentation. Again, we're a little bit slow on the ground with questions, so I would like to invite the participants to pop their questions in the chat box. But to start with, so I'm quite curious, what sort of technologies are you using to actually detect the SF6 in the assets?
So at the moment, there's different technology being used. The most accurate one is to have pre-installed density sensors, so they can record the exact volume inside, and also pressure sensors to monitor the leak. But those ones, the problem is they record the data for a 6 months period, and then it's get overridden because of data storage issues, like with many sectors at the moment. So the issue with that is it doesn't give you, so you saw from the leakage profile, you can only see a trend over sort of a 50-year period. So with 6 months, it's very difficult to make that assessment. So that's where we need a bit of automation and maybe a bit of machine learning as well in there to look at the leakage profile and forecasting of leakage going forward.
Yeah, I was going to say there seems to be a really good opportunity here for some AI technologies to come in to help with those analytics, and also perhaps maybe some innovation in data collection processes and things like that. So for the innovators on the call, make a note of that. There are opportunities here. We have some questions coming in. Is there much activity in SF6 recycling within transmission and distribution networks? And is this considered within your project?
So currently, I think one of the main suppliers for this, for National Grid, is Celtic Recycling Ltd, based in Newport. So they do taking a lot of the used SF6. There's some challenges because some of the toxic byproducts cannot be easily filtered, like S2F10 and CO. So potentially, as you recycling, you're getting a buildup of very highly lethal toxic byproducts. So these are issues that we have to look into. In terms of consideration in this project, what we're considering is more method of sort of low carbon approach to incinerate the gases in the future, as we kind of move into a phase where we basically no longer need to use SF6 going forward. Thank
you, Tony. So I have a question from Rob Walden here. do you have any telemetry that tells you that there is a leak or that a leak is developing? And does this data get sent OTA to a monitoring center?
I'm not sure it's that sophisticated. So I've been to substations where literally is hand recorded on a piece of whiteboard how many kilograms of SF6 top up. Generally, all these substations that will have the equipment will have a low pressure monitoring alarms. So that will obviously trigger, and then the operator then need to top up the SF6. And by regulatory requirements, because this is a very potent greenhouse gas, you have to record how much you top up. So that's generally the moment here. So I mentioned some have a continuous monitoring, but it kind of is for a 6 months period before the data get overridden. So it helps for you to make local assessment on where the leak is and how the leak is developing, but it doesn't allow you to have that historic data and allow you to really forecast. So when you look at the forecast scenarios, it's very much like almost a linear increase if no interventions, and if with interventions, it's a percentage decrease. It's not that automated, I would say. Yeah.
And just a second part to Rob's question, does the 6 month data collection struggle with seasonal variance at all?
That I'm not quite sure. So when we went to the leakage data, we didn't see a real trend between winter and summer, whether there was more top up or less top up, if that was the question here, if I understood the question correctly. Okie
dokie. And one last question from AO. Is the plan to produce a decision-making framework for choosing intervention strategies? And if yes, will it be transferable to the distribution network level?
So the first one is absolutely the plan here, because there's not enough, I think, investment that can be made to replace everything in one go with a new build. So we'll have to a look at different intervention strategies. And the second question is yes as well. The first is focusing on transmission because it's where the greatest win is, and then moving to distribution level going forward.